Good evening, everyone. Thank you for joining us tonight in a design talk titled Hybrid Intelligence, Architectural Robotics Beyond Machines with Dr. Sina Mostafavi.
Okay, thank you so much, ArchiNet and the team, for inviting me to this lecture. I'm excited to be here. The title of the lecture is Hybrid Intelligence, Architectural Robotics Beyond Machines. I'm going to mainly talk about computational material and fabrication intelligence in architectural materialization processes. I'm Sina Mostafavi, Associate Professor at Texas Tech University, Huckabee College of Architecture, and I'm honored to be here. So my background stretched to different countries where I've been an architect, scholar, researcher, and professors. I'm originally from Netherlands and Iran, where I've also done my master degree and PhD degree. I graduated from TU Delft with a doctoral degree, and I've worked in TU Delft, Bauhaus University in Dessau, the Institute of Architecture, and I've worked also in UK. And recently, I'm associate professor, and currently I'm an associate professor at Texas Tech University, Huckabee College of Architecture in the US. So my lecture today is divided into three main parts. I will give you a kind of a general context and background of what I called architectural materialization, architectural robotic materialization. And then I'm going to discuss three core methods with several projects. I would call them three main concepts of architectural robotic materializations. Then I open up the lecture with some recent projects and case studies to provide a kind of a vision and about the future of the pedagogy and practice. So I start my lecture with a series of questions. How can we associate different performance criteria with topological and geometric variation? Like on the left, where in the music hall, variation in size and depth and shape of cavities result in a better acoustic performance of the space, and how the use of emerging digital fabrication technologies with which we can afford significantly higher level of resolution, as you can see on the right, allow us to achieve better performance considering different criteria such as structural, environmental, and functional. While we are designing, how can we look beyond the finished and commercial building products or materials by looking into sequence of construction and constraints and potentialities of different production setups? How can we learn from the history of craft and construction, and what other industries such as automotive industry have to offer to architectural production? How do we build livable spaces? Which methods may be used? For instance, what are the fundamental differences between subtracting a material out of a mass, like the case on the left, versus adding or assembling matters or elements to build up the target design, like the case you see on the right? And how may these different building methods result into new models of materializing architecture? And how may they alter past and present applicable models or future visionary models feasible? In this context, which is materializing architecture, what is the role and impact of design media in general, and representation, simulation, and computation technologies in particular? In an interdisciplinary setup, what role designers and architects can play to develop advanced and tailor-made design media for more efficient products that may save lives and matters? How do we assess the constructability of a particular design? Is more visually geometrically simple, more constructible and cost-effective? At least in the case of this monumental building, the answer seems to be no, as the curve on the left, as you can see here, is defined by simple straight and circular curves, while the more constructible curve on the right might seem visually and mathematically more complex, because with a simple formula, we can address any point in space. How can we benefit from geometric complexity in multiple scales, ranging from very small or micro to very large or macro? For instance, on the left, you can see how a macro scale example where structural stability is achieved by introducing the Sina curve in the structural wall, And the video you see how microstructures in 3D printing results into better stability. So in a nutshell, in general, the question is how emerging technologies are transforming the experience and practice of architecture. But if we want to be specific, we can replace these two words of emerging technologies and architecture with more specific terms. And here we are mainly focusing on architectural materialization, robotics, and what we call hybrid intelligence. In another summary, we can also refer to the notion of tool and media. And with this quote by Marshall McLuhan or John Calkin on the work of Marshall McLuhan, as we see here, we become what we behold, we shape our tools, and then our tools shape us. So the way we shape our tools is also another interest of us. So with this overarching questions, in addition to architectural design and computational design, the main discipline that we are addressing here is architectural robotics, which can be divided into two main categories. One is robotic environments, the environments that are controlled by robots or they are actuated with robotic systems, and robotic production. In this lecture, you're going to see more about robotic production than in robotic environment, but I see these two disciplines very much intertwined and connected. So when it comes to robotic environments, it's about how, by embedding actuatable systems, we can customize our livable environments. For instance, when I joined Hyperbody Research Group at TU Delft, this was one of the very first projects that I've seen where by let's say, creating these smart materials, we can activate a wall to accommodate different functions, so on and so forth. But at the same time, it's about architectural robotics is about how we can create what I call immediate or like instant connection between digital space and physical space. In this case, on one of the early examples of like this, what I call immediate materialization is about how we can translate a 2D, let's say, impressive drawing by an artist into a 3D sculpture, which is carved by a robot. So this immediate connection between the digital and physical is something that we can achieve because of the programmability and customizability of robotic systems. So again, it's about bridging the gap between design and construction by developing integrative design production systems where we have the component of computation, component of automation, and component of materialization in order to create a difference in making and making a difference. Getting towards the second part of my lecture, I'm going to browse through several projects with the categorization that I'm going to introduce later, and then we will proceed to the last part. So this is the framework that I've developed in the past years, which is also summarized in a book written by myself, which is also a summary of the PhD work that I've done in TU Delft. It's about how we can provide a kind of an integrative framework for robotic materialization. Okay, I have divided these into three notions of porosity, hybridity, and assembly, and I'm going to start with the notion of porosity. Porosity is about how we can basically control the mass and void relation in different scales of materialization. So this is a project that I've done in TU Delft, which is about how we can translate the result of topology optimization, which is a discrete method, to a continuous robotic 3D printing. As you may imagine, the result of finite element method is usually discrete, and then by developing integrative design to production systems, we can translate this result into a printable, let's say, continuous toolpath. So we were running several tests and several experimental work on how we can translate this discrete result into continuous toolpaths. And as you can see here, we are trying with different materials, including light or ceramics. And the idea is to basically deposit material in a continuous manner while keeping the material architecture intact. And then we were also customizing our end effector, because working with different materials require different, let's say, resolution. And if you develop your system for ceramic 3D printing, it would be different than concrete 3D printing. So as you can see here, we are bringing the world of material and computation and production together to find an optimum specification and customize our production system accordingly. And this is also based on another project that I've done, which is about, again, translating discrete results into continuous result. And as you can see here, we are translating the discrete result of topology optimization into continuous vector-based geometry, and this result into this method that we were developing using a Python script, which search within the point cloud, that is the result of structural optimization, and in a continuous manner deposit material where needed and as needed. Some similar projects that I have recently done at Texas Tech University also applied a similar workflow and techniques. So for us, it's really important to see how we can think about the agency of fabrication early in the design process and inform our materialization techniques accordingly. The second topic is hybridity, or what I call hybridization of production methods and hybrid materiality. As I said, I see this in two different categories. One is hybrid materials, how we can think of combining and integrating multiple materials. Therefore, we need new computational design workflows and approaches to compute hybridity, especially with the advent of multi-material 3D printing system. This seems to be a very viable and applicable solution. And at the same time, it's about hybridization of production method. And hybridization does not necessarily mean that we are going to hybridize additive or subtractive methods. For instance, we can also think of hybridizing the production techniques by combining two subtractive methods to make the whole process of production more efficient. For instance, in this case, you see how hot wire cutting is combined with milling, and hot wire cutting is only applied where we have developable surfaces, and milling is only applied, wadding milling is only applied where we have curved surfaces. So by hybridizing the production system, we can make the production and design more efficient in terms of fabrication and materialization. I'm going to go to 3 projects addressing the notion of hybridity. The first project is Hybrid Cork, where we are approaching milling in a different way rather than crushing the material. Here, as you can see here, we are peeling off the material. So in this way, we are basically embedding a kind of controlled flexibility in the material, which is by definition hard. And then this controlled flexibility results into basically translating or transforming a 2D material into a 3D bendable material. In this case, use it as an acoustic panel. And at the same time, hybridity is about hybridizing different material systems together. So combining, for instance, concrete, which is a structural material, with EPS, which can be an insulative material. And in this project, we were looking to how we can rethink how we usually see molding or casting. In this case, for instance, we are looking into a 4-part mold instead of a 2-part mold. And then this results into keeping part of the mold as part of the building components, where both of these materials are continuous, and the concrete is holding the EPS in place, because in a kind of a three-dimensional way, hold the two pieces together. And again, another dimension of hybridity is about how we can combine different methods of production together. In this project, we were looking into how we can 3D print silicon, which by definition is a very viscous material and hard to print. And then we were developing different end effectors. And then we were running series of tests, of course, to understand what is the right speed, what is the right design, what is the right material properties. And then this results into a product design project, which is about applying this soft material on a chair, which is called hybrid chair. An overview of the production and design process is also summarized in this. Again, as you can see here, we are interested in developing integrated systems where fabrication is a very strong component in the design process, and it provides feedback loop to what we design in terms of fabrication ability and being able to materialize our design alternatives. As you can see here, the sequencing is also very much important, not only for optimizing the very production process, but also including collisions between the tool and the object while you're designing and producing your piece. Again, the results of these research are usually, research projects are usually documented in peer-reviewed publications, which you can find later in the link that I'm going to share or in my website. And the third component is assembly. So we had porosity, hybridity, and assembly. So architecture, in contrast with other industries like automotive or electronics industry, is something that is usually bigger than the size of the production setup. So what I call assembly intelligence, or the notion of component and sequencing in construction, is going to be very much important. So part of assembly is about how we can embed, let's say, assembly logic and interlocking logic into our components while we are producing them. And then at the same time, looking into the sequence of assembly using robots. So for instance, in this case, you can see that we are using a very known method of stacking, but at the same time, we are looking into stacking in such a way that while we are stacking the elements, at any given time during the production process, the stacking is stable. So this requires basically embedding the constraint. And again, it's not only about constraint, but also the potentialities of the fabrication system and the very physics of the work that we are proposing to the design to production process. Here is another example of assembly intelligence, where I also borrowed this notion of one building, one detail from Klaus Osterhaus, where it's about like having one detail, but also varying that detail in such a way that like with one system, which is programmable, we can produce ranges of components which are different, but the production system, since it's programmable, allow us to create the complexity that benefit us in multiple fronts, including structural stability or structural optimization. This is 100 years Bauhaus Pavilion that we Design and Produce in 2018, which is about, again, looking into the milling, not in a conventional way, but looking into the milling in a way that also is considering the fabrication potentials of a 6-axis robotic, 7-axis, in this case, robotic production cell. And then we were looking into also the way we can use reciprocal system on a complex freeform surface, and then we develop our own tessellation system. Again, the results are also documented in a peer-reviewed publication in ICADI 2018. Sorry, it was 2020. Again, you can find the link to the book, which is summarizing these projects and provide a kind of an insight about robotic materialization. You can use this QR code to access that information. Moving towards the third part and the last part of my lecture, which again will be a pileup of several projects that we have been doing in the past years. I would like to provide a kind of several statements and vision about the future of pedagogy and practice, considering what I call hybrid intelligence and these new methods of robotic materialization. So I have divided this part of the lecture into 3 subcategories, what I call integrative design, which you saw some examples in the previous project as well. And this notion of applied versus experimental, which I think is very, very, very much important in today's world. We need to acknowledge the difference between applied and experimental work, but I find both cases important, and the notion of interdisciplinarity or interdisciplinary work. So when it comes to integrative work, again, it's about how we can benefit from complexity to enhance the performance of our building components, and being able to work with higher resolution of design and production systems is something that can benefit us in terms of providing and producing efficient components and efficient production systems. So, and usually measurable criteria such as structure or environment are easier to map, but I would like to argue that it's not only about like structural or environmental parameters. Another, I would say, job of architects of today is to see how less measurable, let's say, criteria such as functions or environmental comfort can be also become measurable, and then we can benefit from the complexity that we can achieve through robotic production. So here you see another example of metal forming, which we are using a bendable material, which is a 2D material, and by creating the complexity where needed, we are enhancing the structural performance of each element. So if I want to provide a kind of an overview, it's about how in multiple scales, using multi-mode robotic production systems and using multiple materials, we can afford to develop a multi-criteria design to production system. And it's also about how a very complex process of production can be basically translated into a programmable system. So this is, to me, one of the very early examples of computers using punch cards to basically weave this is a loom machine to systematically basically translate a very complex production system into a programmable system. And it's not surprising to see how the very early examples of punch cards are similar to what we see, what we saw in that loom machine. So in a way, the whole production system becomes almost like a surgery, if you would like to call it that way, where each component where we can map and predict the production process of each component. This is where simulations become very much important. And it will be very much about how we can learn from every single experiment that we do in order to basically create what I call families of objects. So as you can see here, all these components, most of them are I-shaped. So topologically speaking, they're similar or identical, but geometrically speaking, they are different. Except, for instance, this component here, which is a Y shape. But learning from all these simple I-shaped components, we were able to understand how, for instance, we can also produce a Y-shaped component and eventually also produce an X-shaped component. So what I would like to say is that, so it's about like developing this integrative system in such a way that we can map the constraint and potentialities of each system, and then be able to produce what I called, again, families of objects. So in a way, in summary, it's about how we can bring material space, design space, material space, and production space together and explore them simultaneously. The second part, which was about applied and experimental, I would say to a certain extent, what we do in academia is also informing what we do in practice, and vice versa. So for instance, this is one of the buildings that I've done through my practice setup architecture. In this case, we were not using necessarily a robotic production system, but learning from this notion of hybridity, we were interested to see how we can basically use stone construction in a different way by combining the higher accuracy that we can get, for instance, in metal bending and laser cutting the basically metal pieces and bending them with a less accurate material, which is natural stone. And this results in a kind of a hybrid material system where each element is stacked in a discrete way on top of each other. And here we were also interested to develop a kind of a material language or material culture where we integrate the facade, landscape, and also other interior and exterior components of the projects. Which brings me to the notion of resolution. Again, while new methods of construction may allow us to work with higher resolutions, I don't think it's only about like increasing the resolution, but it's about how we can find a proper resolution according to the materialization system that we develop, and then embracing that tectonic or that materiality in our design process. And at the same time, I would like to argue that although technology is I would say, placeless and universal phenomena, we are not detached from our, let's say, cultural backgrounds. So one may argue that the very building that you saw here is about like digitalization and computation, but at the same time, it's about the very culture that each of us as architects are coming from. And when very early examples of generative AI became more accessible through platforms like Midjourney, it was really interesting to see how the very cultural aspects of what we call architecture and materiality is embedded in the data that is accessible to everyone, and how we can be aware of what I call cliches and biases to some extent, but also cultural constructs And this is these are some explorations that we have done using Midjourney AI and generative AI. And a recent work of us together with another colleague of mine, Professor Mehan, was about to see how these very cultural and social aspects of digital information that is there in the internet is resulting into what we called in our recent paper visual cliches and verbal biases. And it's really important and interesting to be aware of these, I would say, cliches and biases, and be aware of that when we are designing and using these new technologies. And it is not surprising to see how, for instance, this memo was basically generated or developed and shared by this platform about that very project, Softstone, that I shared. It's not surprising because I'm from basically the generation of Windows 95. So in addition to all those cultural backgrounds to that project, I would argue that the very digital culture that we have now and we have been grown up with is also part of what we are as architects of today. And it's also about, as I said, not only the very, let's say, contextual cultural background, but it's also about the way the digital is creating a culture for us. For instance, this is one of the very early examples of games that I used to play. So as you can see here, it's very simple, but beyond the fact that this is a very simple game, for me was really interesting to see how a very simple formula is creating a very simple simulation here. And of course, in the studios, especially like in the thesis studios and graduation studios, I'm interested to see how these integrative systems can result into a more, I would say, game-based scenarios where we are developing integrative design to production systems, not only addressing materialization, but also addressing social aspects.
Let's go to a place
which is beyond
where everything is made of blocks.
The materiality. These are some of the examples of, again, incorporating the notion of context and culture into materiality. These are some of the examples of the studio work in Bauhaus that I've led. So back to the notion of applied versus experimental, I would argue that it is important to be aware of the very experimental dimension of these technologies, but at the same time, see how these visionary, let's say, results can have an impact into real world problems. Like, for instance, in this case, the students were looking into the favelas and developing an app for changing the landscape of favelas to an urban farming situation, and towards a more applicable solutions. The notion of circularity or reusing is also another important aspect when it comes to applied versus experimental. So this is a student of mine in TU Delft, where she's looking into basically reusing plastic boxes from construction industry, and then running several tests to see how we can develop joints using robotic cutting, or in this case, a colleague of mine, we were looking into the way we can embed a kind of self-assembly intelligence for translating a 2D material to a 3D structure. So in a sense, in summary, in many levels, the data is the new materials that we are working with. ranging from art to the city scale. Based on this, we were also running several experimental projects. For instance, in this case, we were looking into how brain waves can be directly translated into art pieces. So this notion of personification is also something that can be important. Or we were looking into how by quantifying the data from the way we are basically navigating a city, we can create, again, art pieces. These are more towards the experimental notion, but these very small modules of experiments sometimes become a larger component for a larger project. So that's, I would say, important in our pedagogical and practice and professional framework when we are using these systems. Or in another project, they were looking into the way the facial recognition can result into different artistic expressions, while these are more toward the artistic front of what we have been doing. I believe these really small components can also later become a component for a larger project. Another notion is the notion of human-robot collaboration when it comes to interdisciplinary work. So I would argue that the next generation of robots in architecture would very much be about how we can collaborate with different types of robots and how we can build our own robotic setups where human and robot can seamlessly collaborate. In these projects, which we did in collaboration with Materiality Lab of the SETUParchitecture Department of Design, together with the SETUParchitecture Institute of Architecture students, we were looking into discrete assembly systems where we were using a soft robot, in this case an EVA, and then we were looking again how we can, for instance, develop again components which are proper for these types of robotic systems because they are softer, and then we were benefiting from this softness to basically assemble this complex structure without using glue or an additional material. So in a way, in terms of how these new methods of materialization, or again, what I call hybrid intelligence, is changing the landscape of architectural pedagogy, you would barely find me giving lectures like this. It's very much about collaborating with students and researchers and also people from different disciplines to, on the one hand, hack the robotic systems and benefit from this programmability, but also it's about how we can answer to this very, I would say, important question. Are we interested in developing what I called androids, which are robots that are similar to humans, and they are repeating the tasks that we have been doing in the building industry over and over? To me, the way this robot is putting this panel in place, it's funny. And I would argue that the robot is suffering a lot because rather than repeating what we were doing over and over for years, we may need to rethink the design and find design solutions which are more proper for integrated design to production systems that are developed by architects and for architecture, rather than letting engineers basically develop androids like this that are trying to repeat the task that is probably done by a human in a more smooth way. The last part of my lecture, as I promised, is about interdisciplinarity. I'm gonna have two or three more projects. The first project is the Audi projects that we did again with collaboration with Materiality Lab. and also my unit Dars Hub in the Science of Architecture. It was really interesting to see how architecture can stretch its reach towards other disciplines. This project was sponsored by Audi. They were interested in developing new, let's say, configurations for a city car, where people can sit inside a self-driving car and interact. And also, we were interested to also incorporate nature into the body of the car. So this, in some way, summarized the whole process of production and integrating sensors and actuators into the whole system. And it was also really interesting to see how, again, architects and designers can collaborate together to achieve something which is beyond the scope of traditional scope of architecture. And here you can see how we were incorporating sensor and actuators, in this case, also using simulation techniques to optimize the body of the car, and also integrate, again, different sensors and actuators, smart glasses, and smart lighting systems to the whole body of the car. And at the same time, the notion of interdisciplinarity is going to be very much beneficial, especially if you want to develop new material systems. In this case, we were developing ranges of bioplastics and customizing then using parametric modeling or generative design, customizing the material systems based on different production technologies that we were using. For instance, in both of these two cases, we are using bioplastic, but the very bioplastic that you see on the right is customized for cutting, which results into a kind of a porous structure on the right to transform a 2D material into a 3D, versus customizing the material and production system for 3D printing, where by learning from failures, we were eventually able to customize the material recipe for bioplastic robotic 3D printing. This research has been advanced by a very good colleague of mine, Benjamin Kemper, who's doing his PhD on bioplastic robotic 3D printing in collaboration with ETH. The last project, which I'm going to show, is a recent project of us called Fabricity XR, which is a collaboration between the studio that I was leading, Design Competition Fabrication in Texas Tech University, together with the studio that Professor Mehan was leading on urban community development. In this project, we were interested in the notion of hybrid of digital and physical, or what is phygital environment. So we were looking into the ways we can map digital environment onto the physical environment. This project is currently on the display in Venice. So it is, again, with an emphasis on interdisciplinarity. It is bringing 3 disciplines together, which I'm going to explain later in the next slide. But it is about how we can map digital information into a physical environment in order to create a kind of an immersive experience for the users, where potentially the digital environment can also be modified in real time, and this create a new experience or a new immersive experience of what we usually see with only physical environments. As said before, in this project, we are bringing different disciplines together, and the scope of the projects are mainly 3: design, computation, fabrication, urban community, and spatial justice, and extended reality or gamification, which is about this phygital space that I mentioned, which is about hybridization of digital and physical environments. And as said before, this project is currently on the display in Venice, in Palazzo Mora. If you happen to be there, you can visit it. It's going to be exhibited there and stays there until November 2023. And with this video, I would like to wrap up my presentation, where we are using HoloLens set to assemble the structure, again using the phygital environments that we developed for assembly. Yeah, and thank you very much. Again, you can find more information on my website or through the social media links that I provided here. And I would be happy to take any questions or
thank you, Dr. Sina, for
further
this
discussion.
informative lecture. I believe we already have some questions. We'll start with Luai. How do you apply computational design and material fabrication on large-scale buildings? In which parts of the buildings?
Well, that's a very good question. So I think what we see as fundamental research in academia may impact industry in different levels. For instance, in the last project that you saw, we were collaborating with a 3D printing company in France, X3, where they are developing concrete 3D printing in large scale fabrication, for large scale fabrication. So I would say techniques such as 3D printing or robotic assembly are techniques that we can use in building industry, and we see examples of, for instance, 3D printing neighborhoods also in, for instance, in Texas by a company called Icon. But beyond the very first applications by industry, I think it is important to be aware of how what we do in academia can have a larger impact in terms of circularity and sustainability in construction. So how we can minimize the carbon footprint of a very, I would say, carbon intensive materials such as concrete. So, and that's why, for instance, it's not only about like advancing the very machinic aspect of technology, like developing new robotic setups, but it is also about innovating in material systems and material recipes, using alternative material systems which are more sustainable. And when it comes to computation, I think educating the next generation of architects with computational design knowledge is going to be very, very instrumental, very much important, because I would argue that computational design knowledge to some extent should be the background knowledge, and the goal should be beyond that. The goal should be about circularity, the goal should be about sustainability, and how we can basically with less energy and less material, we can create a more friendly and more performative environment.
A question from Khaled. Can you explain the differences between hybrid intelligence and traditional artificial intelligence?
Yeah, that's a very good question, actually. So I would say, so we have we have several notions. Maybe it's important to address these notions and see how there are somehow subcategories of each other. So for instance, we have the notion of machine learning, and we have the notion of deep learning, and we have the notion of artificial intelligence, and we have the notion of computational intelligence. And then we have the notion of hybrid intelligence, which I'm interested in. So machine learning. So I would also like to start with these notions, which are a bit niche to some extent in today's world. I would say computational intelligence to many extent cover artificial intelligence, deep learning, and machine learning, because computational intelligence can be any form of intelligence which is achieved through use of computation, right? So in that way, artificial intelligence will be under the notion of computational intelligence, and it goes beyond what we see as generative AI or artificial intelligence. It's a larger, let's say, umbrella that sort of cover these topics. Hybrid intelligence for me is where through use of systemic thinking, we can combine human and machine intelligence. And in this case, machine intelligence is both physical machines, like robots, like physical robots, production machines, but also is computer as a machine, because computer is a machine. And if you think about it, a computer is a programmable machine, like a robot, which is a programmable production machine. And hybrid intelligence in this context is allowing a human as an active agent to be the decision maker within the design and production process. Of course, when we are talking about architecture, we always deal with design and production. So in a way, maybe opposite of hybrid intelligence is full automation or fully automated decision-making process, where we try to use any sort of computational intelligence. It can be optimization, it can be artificial intelligence, and we only rely. We also need to consider the fact that still human is the author of those systems, right? But we can have two types of systems: a system that start the process from the point A and then end it in the point Z, and human cannot interactively change the system, versus using hybrid intelligence, in which the system is designed in such a way which is open for intervention of human. And in this case, I think there are some important areas for investment or in explorations. One is assembly, because I believe humans are way more smarter in many ways when it comes to assembly. You may, because you as a human have, first of all, has a sort of a pre-programmed knowledge about how things are going to be assembled together, or you know that you have to put your cup on a specific spot. That somehow can be programmed using artificial intelligence. But beyond that, I think assembly is one of the things that we can invest when it comes to hybrid intelligence. And another area is, in many cases, using common sense, which when it comes to design and architecture, common sense and rational thinking is also, or critical thinking is also something that maybe pure artificial intelligence or pure computational intelligence may miss or lack.
We have from Majid Al-Banna. Greetings, Dr. Mostafavi. I had the honor of being one of your students in DASO, and it's good to hear from you again. The question is, has there been any attempts or researches in using AI to directly fabricate using KUKA arms or generating art pieces using 3D printing, similar to how Midjourney can generate images in pixel space? Would love to hear your opinion.
First of all, hi Mag. I clearly remember you. So as one of my good students, and thanks for your question. That's a very, very, very interesting question. So because, and actually that's a question that I'm trying to address in a publication that I'm working on. So the question can also be summarized in a way to this question that will generative AI, because like Midjourney is using generative AI systems, can generative AI create materials? I mean, when I say create, it's partially digital creation, creating maybe point clouds which are informed, and there are digital materials, but also create using robotic systems. So an answer to this question to me has two parts. One part is about how we can, again, like the way we were showing in the projects, basically bridge the gap between digital design and physical production, and how we can incorporate materiality in these bridges. So how we can, for instance, digitalize a material system, for instance, by maybe I can refer to the notion of Maxcel, which is a material pixel or material voxel. So when we are using generative AI and create 2D images, we are creating pixels. When we can also create 3D objects, but these 3D objects are either meshes or they're point clouds. If there are point clouds and in any given point in the space, we can also incorporate material properties, we can be one step closer to also create a database where we then can use, let's say, artificial intelligence or generative AI to create materials for us. So therefore, as I said, there are two parts. One is bridging the gap between design and production. And the second part is creating a database. You asked whether there has been an attempt. There are some recent attempts using generative AI to create 3D objects. I know there are some researchers in, I think, Singapore University. There are, I think the name of the professor is Professor Emmanuel Ko, who is using also generative AI to create 3D voxelated, let's say, objects. But then the next step is to how we can also create a production machine that can read that information and create, let's say, building components using these digital information by mixing materials, and then which results into new materials that we haven't seen before, basically.
Okay, one last question from Khalid. What are the limitations and potential drawbacks of using hybrid intelligence in the field of architecture?
That's a big question. So maybe that's a question.
Another lecture.
Another lecture, or it's a. I mean, but it's a very good question to ask, right? So, well, the limitations. Let's start first from the limitations. The limitations. It's about whether we are asking about the limitations and whether we are mapping the limitations in real world and building industry, or are we mapping the limitations in pedagogy and education? So I think to some extent in education and pedagogy, there are some limitations because depending on the pedagogical model that you develop, since you are developing a new field and you're exploring new fields, there might be limitations in terms of learning curves, in terms of resources for learning, so on and so forth. But when it comes to industry, it's about how I would say knowledge-driven and knowledge-based companies and startups can bridge the gap between what we see as niches or academic niches in the academia and the actual technology that we have available in the industry. So the role of startups and innovation in the industry would be very much important. So like if you think about it, like 30 years ago, thinking of 3D printing architecture in real world was off the table. But now, since there has been companies that were trying to bridge the gap between academia and practice, this becomes more real and accessible. And the same things goes to, I mean, this notion of hybrid intelligence or human-robot collaboration. There need to be new frameworks when it comes to ethics, when it comes to safety, which might not be there. So you saw, for instance, with the advent of generative AI, the European Parliament, or like
yes,
in the US or in many other countries, they were trying to reinvent or rethink the way the law or regulations are framing this new technology. So the answer to the question is beyond the very thing that we do in the industry or practice. Is also, it's about how a larger in larger scale the society and governments would pick up these new emerging technologies.
I think we can wrap up now, Doctor.
Thank
it was
you so
few
much.
questions, but was long ones. We really appreciate your participation today, and the lecture was very impressive and informative.
Thank you so much.
I'm looking to collaborate very soon. Thank you.
Sure. Thank you so much.
Have a good day.
Bye-bye.
Take care.
You too.
Bye-bye.
Bye-bye.